Today, I will show you how to render a triangle inside our Win32 game window, the foundation of every 3D object in video games. This is your first step toward real-time graphics and custom rendering. Create a class called Renderer. There we put everything related to DirectX. It only has a few public methods, but that's all we need for now. Commands for clearing the screen, uploading geometry to the GPU, and rendering the geometry. Now to the actual initialization of DirectX. This is all happening inside the constructor of our renderer class. There exist two main DirectX objects that we must create. One is called the device, and the other one is the device context. The device is needed to create resources such as vertex buffers, textures, shaders, etc. The device context allows us to send actual commands to the GPU, such as clearing the back buffer, binding shaders and textures to the render pipeline, and issuing draw calls. We call the function for creating the device, which also creates the device context. Checking the result of these creation functions is important, as these might fail. In our case, we exit the game immediately if this happens. It does not make sense to continue without a valid DirectX device. Next comes the creation of our swap chain. A swap chain handles rendering to multiple back buffers and then shows the result in our game window. We can configure things like how many back buffers we want, the color format, multi-sampling, and the presentation behavior. We call create swap chain with our desired settings and check the result for failure. Next comes the resizing of the swap chain and creation of the so-called render target view. I have put this into a separate function so we can reuse it later, when we need to react to the user resizing our window or changing the resolution when in-game. We then create a def stencil buffer so we can render the objects correctly sorted by their distance from the camera. The def stencil buffer is basically a specially managed texture, which is configured to be used for the def and stencil testing. After creating the underlying texture, we fill out a def stencil descriptor. We turn on def testing and declare that only pixels with a value that is smaller than the current value in the def buffer is accepted. This is the basis of the cbuffer algorithm and allows for correctly displaying objects without the need to sort them by their def value before rendering. What is closer to the camera wins. The actual def stencil state is then created and we set it to be the current valid def stencil state on the GPU. After all these swap chain operations, all that's left is creating some default states within the GPU for rasterizing, texture sampling, and blending. Let's look at these in more detail. Rasterization is how the GPU fills the space where triangles are drawn on the screen. By filling out a rasterizer descriptor, we can instruct the GPU to fill the triangles with solid colors or to just render the outlines, something we also refer to as wireframe mode. In addition, we also set the culling mode here. Culling is when the GPU omits surfaces which face away from the viewer. This is good for performance as pixels are not rendered which would be invisible anyway, for example, interior faces of a closed cube. Now we create a sampler state. It tells the GPU how we want our textures to be processed. For example, we set what should happen if our UV coordinates exceed the value of 1 in any dimension. In this implementation, I tell it to just wrap around. Another important attribute is the filter. Here we decide what should happen if the resolution on the screen is not exactly the resolution of the texture itself. If you want to achieve this crisp pixel art look, set this to point. Otherwise, linear is smoothing out between the neighboring pixels. On to the blend state. Here we decide how new pixels interact with already existing pixels in our back buffer. An example. Let's say we render two triangles, and parts of these triangles are overlapping. Now what should happen in these overlapping parts? Should the pixels which are drawn second just override the pixels which had been drawn first? Or should the first drawn pixels always be kept? Or should we mix these two pixels together? We will go into more detail on this in later episodes. For now, we make a basic setup which allows for transparency to work. Back in our renderer constructor, we finally bind our back buffer, telling the GPU that our next render command should write to our default back buffer. Later, when we use separate so-called frame buffers for post-processing effects or minimaps, we will bind these frame buffers separately. We're now finished with part 1, and the basic DirectX settings are in place. So on to the next step. To render anything with DirectX, we must give it the underlying data of our geometry. In the case of a triangle, it is exactly 3 vertices, where each vertex represents the position of a corner of the triangle. Before we can upload any vertex data to the GPU, we must prepare vertex buffers. These buffers live in the video RAM, and you can imagine them just like arrays in memory. To create such a vertex buffer, we first define some properties such as the size and the intended usage. Then just call createBuffer on our device object and we are good to go. Next, I show you how to use this function. We simply define the actual corner positions in clip space coordinates with a local vector. Then we call our createVertexBuffer function and pass the data. Now the GPU has stored our precious triangle position data and we can move on to shaders. Shaders are little programs which run directly on the GPU. They are part of what we call the programmable stages of the render pipeline. Here is a very simplified version of it. Every time a render command is executed, our vertex data is processed through these pipeline stages. Some of them are fixed, so we cannot change them with shaders. Some of them are programmable, and these are where we use our little shader programs. For this tutorial, we will make use of 2 shaders, a vertex shader and a pixel shader. The vertex shader is responsible for manipulating the incoming raw geometry for a given object and transform it so it ends up in the desired place on the screen. The pixel shader then provides the color. Later we will take the color information from a texture image, but for now we will just provide a single color value. Let's take a look at our actual shader code now. On first sight, it looks quite similar to C code, so we should be able to understand what is going on. Every shader program has a main function, which acts as the entry point, called by the GPU. Here we create an instance of our output struct, which we have defined above. In our case, this is just describing the position data we have been uploading before. In our simple case, we do not make any matrix transformations with these positions, so we just pass them on to the output, unchanged from how they come in. The pixel shader is also very small. It declares the output from the vertex shader as its input parameter and returns an RGB color value. In our case, this is a nice saturated orange. Now, these shaders must also be uploaded to the GPU, just as our geometry data before. For this, I have prepared separate classes to represent shaders and shader programs, which are just a combination of a vertex shader and a pixel shader for now. Later, we may use different combinations of all kinds of shaders, so this should come to good use. Shaders must be compiled, and we do this inside our shader constructor. We give the compiler a few instructions, such as which shader version to use, pass it the code as a string, and call the compilation command. After checking for any errors, we upload our compiled shader binary to the GPU by calling the respective createShader function on our DirectX device. We're almost done now with preparation. Next and final step is invoking the actual render command. To actually render an object to the screen, 3 steps must be followed. First, binding resources. Second, the draw call invocation. And third, flipping of the back buffer. Let's look into each of these and what they exactly mean. We must tell the GPU which of our vertex buffers, textures, shaders, etc. to actually use in the upcoming render operations. For now, we only have exactly 1 vertex buffer and 2 shaders, but later, when we write an actual game, we will have several of each and also some textures. So we must let the GPU know which ones to use now. This is called the binding of resources, and we do it in our doFrame function. As the name suggests, this function is called once per frame and, for the moment, just renders our triangle. So, first we bind our shader program, we bind the input layout and vertex buffer, and finally we call draw triangles, which invokes the render pipeline and draws our triangle to the back buffer. To actually see something in our game window, we must do the final step, which is called flipping the back buffer. This presents the contents of the back buffer in our game window. It is called flipping because what is happening is that when our game window actually attached frame buffer is essentially flipped, the former back buffer is the new window frame buffer, so we can see its contents. And the former window frame buffer is now the back buffer for the upcoming frame. This flipping then goes on and on every frame until our game stops. Let's have a quick peek into these functions before we give our little program a test run. Bind shader is really simple. We use our device context to set the vertex shader and pixel shader. That's it. Binding the input layout is also not a big deal. We just call the respective function on our device context. Bind vertex buffer is similarly unspectacular. We just need to package our vertex buffer into a little vector and then use our device context to set it. Draw triangles is also very lean and simple. First we tell the GPU that it is triangles that we want to render. There are indeed options to render lines and points as well, but these are rarely used, and as we said, for solid 3D objects, triangles are the way to go. Finally, we call draw on our device context object, pass it the number of vertices and our starting vertex, 0 in our case, and this is it. We now can give it a test run. Clicking our debug button, everything is compiled in the background and our game is starting up. And there we have it, our wonderful little orange triangle in all its beauty. We now have achieved a big step towards making a real game. We can now render real GPU accelerated geometry to our window, and only the sky is the limit. When you can render one triangle, you can also render thousands or even millions of them. And the nice thing is, the basic setup stays always the same. In our next episode, we continue our journey and learn how to import models from Blender. If you enjoyed, please like and subscribe. Thanks for watching and see you next time.